Hello friends, we start a class on sequence of function. This is our 8th class, okay? So 8th class. In the previous class we discussed two consequences of uniform convergence and some examples. In this class we discuss another consequence of uniform convergence and the proof of the theorem and some examples on the consequences. Okay, so we discuss a theorem and some examples. Okay, some examples. So first write the theorem. Let D subset of R and D not equal to phi for each n belongs to n, Fn from D to R is bounded on D. Okay, if the sequence of function is uniformly convergent to F. Okay, if the function be uniformly convergent to F on D, then the limit function f is bounded on D. Okay, so the theorem says that if every term of the sequence of function is bounded, that is, each fn is bounded on D and the sequence of function is uniformly converges to f, then the limit function is also bounded. If each fn is bounded on D and if the sequence of function is uniformly converges to f, then the limit function is also bounded. Okay, so we discuss the proof. So given that the sequence of function is uniformly converges to f, so by definition for each epsilon greater than 0 there exists natural number k belongs to n such that mod of fnx minus fx is less than epsilon for all n greater than equal to k. Okay, this is true for every epsilon. For every epsilon there exists natural number. So for epsilon equal to 1 there exists natural number, say m. Okay, such that mod of fnx minus fx is less than 1 because our epsilon is 1 for all n greater than equal to m because here m exists. Okay, so fnx minus fx less than 1 for all n greater than equal to m. So for n equal to m, mod of fmx minus fx which is less than 1. Okay, fmx minus fx is less than 1. Okay, now since for all n fnx is bounded, okay, because of this for each n fn from D to R is bounded on D, so for all n fnx is bounded, so for n equal, so therefore fmx is bounded on D, so there exists b greater than 0 such that mod of fmx is less than equal to b for all x belongs to D. Clear? By definition of boundedness. Okay, so now we find mod of fx. Okay, this is equal to mod of fx minus fmx plus fmx. Okay, clear? So this is true for all x belongs to D. Okay, this is true for all x belongs to D. So now we combine these two. Okay, so mod of fx is equal to, we subtract fmx and add fmx. Now by triangle inequality, fx minus fmx plus mod of fmx. Okay, so this is equal to, this is a non-negative term, so we can write this. Okay, this is less than 1 for all x belongs to D, and this is less than or equal to B for all x belongs to D. So this is a less than 1 plus B for all x belongs to D. Okay, so therefore mod of fx is less than B plus 1. This is say capital M, and say okay, for all x belongs to D. So here M is greater than 0 because of B is greater than 0. So B plus 1 is also greater than 0, that is M greater than 0. So there exists M greater than 0 such that mod of fx is less than M for all x belongs to D. This implies f is bounded on D. This implies f is bounded on D. Okay, so we prove f is bounded on D. Okay, now we discuss a note. Okay, note: let the sequence of function fn be a sequence of function on D. Okay, let the sequence of function fn is pointwise converges to the function f. Okay, clear? The sequence of function fn is pointwise converges to the function f. Okay, then number 1, let for all n belongs to N and x0 belongs to D dash, let x0 belongs to D dash, then if limit n tends to infinity, limit x tends to x0, fn x. Okay, if there exists x0 belongs to D dash such that this is not equal to limit x tends to x0, limit n tends to infinity, fn x. Okay, this is the equality of the consequence of uniform convergence on limit. Okay, so if there exists x0 belongs to D dash such that this limit does not interchange, that is the limit this is not equal to the limit this, then the convergence is not uniform. Okay, clear? If there exists x0 belongs to D dash such that this limit is not equal to this limit, then the convergence is not uniform. Okay, number 2, if each fn is continuous at a point C belongs to D, but f is not continuous at C, then the convergence is not uniform. Okay, the convergence is not uniform. Okay, number 3, if each fn is bounded, on D, but the limit function f is not bounded on D, then the convergence is not uniform. Okay, so this is by the previous three consequences we check a sequence of function is uniformly convergent or not. Okay, so what is the concept? If fn is a sequence of function on D and it is pointers converges to a function f. Okay, if these limits are not equal, then the convergence is not uniform. If there exists at least one x0, if this is uniformly convergent, then for every x0 this equal to this. So at least one x0 such that this is not equal to this, the convergence is not uniform. Okay, if each fn is continuous at a point C, each fn is continuous at C, but f is not continuous at C, then the convergence is not uniform. If fn is uniformly convergent to f, then and each fn is continuous, then f must be continuous. So if each fn is continuous but f is not continuous, this implies the convergence is not uniform. Okay. Similarly, if each fn is bounded on D but f is not bounded on D, that is the limit function is not bounded on D. If each fn is bounded on D but the limit function f is not bounded on D, then the convergence is not uniform. So to prove a sequence of function is not uniformly convergent, we apply these three concepts. Okay, clear? Now we discuss two examples from mapa. Okay, reanalysis mapa. Okay, so what is our problem? This is block example 3. Okay, this is page number 564, old book. Okay, the problem is for each n belongs to n, the sequence of function is defined by f1x equal to 1 minus nx, 0 less than equal to x less than equal to 1 by n, and 0 1 by n less than x less than equal to 1. Okay, this is our f and x. Okay, we check this is examine sequence of function fn is uniformly convergent or not. Okay, this is our problem. We examine the sequence of function is uniformly convergent or not. Okay, so first we find solution. First we find the pointwise limit function of the sequence of function. Okay, so here each fn defined from 0 1 to r. Okay, here each fn defined from 0 1 to r. Okay, on 0 1. Okay, so for x equal to 0, for x equal to fn x, so for x equal to 0 fn 0, this is a real sequence, so which is 1 1 1 1 and so on, because for x equal to 0 we take this function. Okay, for x equal to 0 we take this function. Okay, so for x equal to 0 fn0 is a real sequence, and the sequence is as this. Okay, so this is converges to 1 as n tends to infinity. So the sequence of function is pointwise convergent at x equal to 0 and limit n tends to infinity fn0 equal to 1. Okay, now for x equal to 1. Okay, now for x equal to 1, for x equal to 1 we get this function, that is 0. So for x equal to 1, fn1. Okay, this is a real sequence, so it is 0 0 0 and so on. Okay, because for x equal to 1, fnx equal to 0 for each n. Okay, for x equal to 1, fnx equal to 0 for each n. So f1 1 0, f2 1 0, f3 1 0 and so on. Okay, so this real sequence is as follows. So this is converges to 0 as n tends to infinity. Clear? So the sequence of function is pointwise convergent at x equal to 1. Okay, and the limit function is fn0 equal to 0. Clear? Now we check if x belongs to 0 1. Okay, if x belongs to 0 1. Okay, so let x equal to c be any point belongs to open 0 1. Okay, we take a point c on open 0 1. Okay, then c is greater than 0 and also 1 is greater than 0. By Archimedean property, there exists natural number m belongs to n such that mc is greater than 1. Okay, by Archimedean property there exists m belongs to n such that mc is greater than 1. Okay, so this implies 1 by m is less than c. Okay, 1 by m is less than c. So if now what is fmx? There exists m. So now we write fmx. Okay, what is our fmx? 1 minus mx, 0 less than equal to x less than equal to 1 by m, and 0 for 1 by m less than x less than equal to 1. Okay, clear? See, this is our definition for fnx. 1 minus nx for 0 less than equal to x less than equal to n, and 0 for 1 by n less than x less than equal to 1. So we take n equal to m. So our fmx is this. Since 1 by m is less than c, 1 by m is less than c. So for such x which are less than 1 by m, for such x which are less than 1, which are greater than 1 by m, fmx is 0. So this implies fmc equal to 0. Clear? This implies fmc equal to 0. Now if n greater than equal to m, this implies 1 by m, this implies 1 by n is less than equal to 1 by m, which is less than c. Okay, now if n greater than equal to m, then 1 by n is less than equal to 1 by m is less than c. So for those n which are greater than equal to m, 1 by n is less than c, that is 1 by n is less than c. So this implies, since 1 by m is less than c, then by the definition of fmx, fmc equal to 0. Here if 1 by n is less than c, then this implies fnc is equal to 0 for those n which are greater than equal to m. So for all n is greater than equal to m. Okay. So we can write fnc. Therefore fnc is equal to 0 for all n greater than equal to m. Okay. So the sequence fnc, this is a real sequence because c is a particular point from 0 1. Okay. So this is a real sequence, and after mth term all term are 0. So 0 0 0 0 0 0 0 and so on. Okay, this is mth term. Okay. From mth term all terms after mth terms are 0. So these are maybe 0 or not. So finite terms are non-zero, maybe 0, does not matter. After mth term all terms are 0. So this sequence converges to 0 as n tends to infinity. This is a real sequence by the concept of real sequence. This type of sequence converges to 0 where infinitely many terms are 0. After mth terms all terms are 0. This is a real sequence, and after mth term all terms are 0. So this sequence must be converges to 0 as n tends to infinity. Therefore limit n tends to infinity fnc equal to 0. Limit n tends to infinity fnc equal to 0. So this real sequence is convergent. So we can say that the sequence of function is pointwise convergent at x equal to c. Okay, and limit n tends to infinity fnc equal to 0. Okay, since c is any arbitrary point in 0 1, we can choose any point. So for every point in 0 1, therefore the sequence of function is pointwise convergent at every point on 0 1. Okay, and the limit n tends to infinity fnx equal to 0 for all x belongs to open 0 1. Okay, because since c is any arbitrary point in 0 1 and the sequence of function is pointwise convergent at c and the limit is 0. So we can take any c in open 0 1. Therefore for every c in open 0 1, if the sequence of function is pointwise convergent at c and the limit must be 0. So we can write the sequence of function is pointwise convergent at every point on 0 1 and the limit is 0 for all x belongs to 0 1. Okay, so our d, what is our d? Our d is post 0 1 and at the point 0 the sequence of function is pointwise convergent and the limit is 1. At the point 1 the sequence of function is pointwise convergent and the limit is 0, and every point in open 0 1, the sequence of function is pointwise convergent and the limit is 0. So combine these three, we can write the sequence of function is pointwise convergent on closed 0 1, and the limit function is fx equal to 1 when x equal to 0 and 0 for x belongs to 0 comma 1. Okay, so this is our the limit function. Clear? Since our fnx is equal to 1 minus nx, 0 less than equal to x, less than equal to 1 by n, and 0 for 1 by n less than x less than equal to 1. Okay, now is the function is each fn is continuous? Yes, each fn is continuous, because since limit x tends to this, only the discontinuity may at 1 by n. Okay, at other point the function is continuous. Only possibility at the point 1 by n. So we check this function is continuous at 1 by n or not. Okay, so first we find limit x tends to 1 by n fnx. Okay, so for this first we find the left hand limit 1 by n plus and limit x tends to 1 by n minus fnx. Okay, so for 1 by n plus this is 0, because then for 1 by n plus we take this function. For bigger than 1 by n, for those x bigger than 1 by n, we take the function this, and 1 by n minus, that is 1 by n minus, that is this. So limit x tends to 1 by n minus 1 minus nx. Okay, this is also 0. Okay, and if n 1 by n is 0, therefore limit x tends to 1 by n fn x equal to 0 equal to fn 1 by n. Okay, this is true for every n belongs to natural number. Therefore if fn x are continuous at 1 by n. Okay, for every n. Okay, so this sequence or this function is continuous at 1 by n, and the other points the function is also continuous. Okay, only possibility of discontinuity at 1 by n. So this function is continuous on 0 1. So therefore fnx is continuous at 0 1. Okay, for all n. Okay, so each fn, this implies each fnx is continuous at 0 1. Okay, each fnx is continuous at 0 1, but the limit function f is discontinuous at 0, but the limit function is discontinuous at 0, but f is discontinuous at 0. If the limit function is discontinuous at 0, but fn is discontinuous, fs is continuous at 0 1, so each fnx is continuous at x equal to 0. Okay, this is continuous at every point in closed 0 1, so it is continuous, fnx is continuous at x equal to 0, but the limit function but the limit function is not continuous at 0. So this implies by our previous note if each fn is continuous at a point C in D, but f is not continuous at C, then the convergence is not uniform. So this implies the sequence of function is not uniformly converges to f. Okay, clear? Now example 5. Okay, mapa, old book, page 564. Okay, so now we write the problem. Let G be a continuous map on 0, 1. Okay, and fn x is defined by gx into x to the power n, x belongs to 0, 1. Prove that the sequence of function fn is uniformly convergent on 0, 1 if and only if g of 1 equal to 0. Okay, G be a continuous map on 0, 1 and fn x is equal to gx into x to the power n for x belongs to 0, 1. Prove that the sequence of function is uniformly convergent on 0, 1 if and only if g of 1 equal to 0. Okay, so let's discuss the proof. First, since g is continuous and this is a continuous function x to the power n. Okay, this is a continuous function because it is a polynomial and every polynomial function is a continuous function. So fn x is a product of two continuous functions. So fn x is continuous. So therefore fn x is continuous on 0, 1 for every n belongs to n. Okay, fn x is continuous on 0, 1 for every n belongs to n. Clear? Now we find the limit function. Okay, so now first we check the sequence of function is pointwise convergent or not. Okay, so at x equal to 0, fn 0 equal to g of 0 into 0, that is 0. Okay, so the real sequence this converges to 0 as n tends to infinity. This implies the sequence of function is pointwise convergent at x equal to 0 and the limit is 0. Okay, now for x equal to 1, fn 1 equal to g of 1 into 1. Okay, that is g of 1. So g, since g is continuous, g is a continuous map on 0, 1 and 0, 1 is a bounded set, closed bounded set. So on 0, 1, on closed 0, 1, g is also bounded because g is continuous map. Every continuous map on a closed bounded set is bounded. Okay, the theorem is every continuous map on a closed bounded set is bounded. Okay, every continuous map on a closed bounded set is bounded. So G is continuous and attains its bounds. Okay, and attains its bounds. This means for every point of the set, the functional value must exist. Okay, clear? So G be a continuous map on 0, 1. This is a closed bounded set. So for every point on closed 0, 1, the functional value of G must exist. So G of 1, this is exist finitely because of G is continuous on closed interval 0, 1. Okay, so therefore the sequence fn1 converges to G of 1 as n tends to infinity, because for every n this is equal to G of 1. So that is the sequence fn1 is G of 1, G of 1, G of 1 and so on. Okay, this is the sequence for x equal to 1. So this real sequence is converges to G of 1 as n tends to infinity. Therefore the sequence of function is pointwise convergent at x equal to 1 and the limit tends to infinity fn1 equal to G of 1. Clear? Now if x belongs to open 0, 1, okay, if x belongs to open 0, 1, then limit n tends to infinity fnx equal to limit n tends to infinity gx into x to the power n. Okay, gx into x to the power n. Okay, so this is independent of x, this is independent of n. So this is equal to g of x into limit n tends to infinity x to the power n. Okay, clear? G of x into eta. Again G is continuous on closed interval 0, 1. Then by this theorem, this is G is bounded. G is bounded on 0, 1. So this is so G of x is not equal to infinity for all x belongs to 0, 1. Okay, so this is not the infinity. Okay, and this limit will be 0 because x belongs to 0, 1, limit n tends to infinity x to the power n equal to 0, because for example, if we take x equal to half, this belongs to 0, 1. Okay, x belongs to 0, 1 means x is a fraction. So if we take half, then limit n tends to infinity x to the power n means 1 by 2 whole to the power n, that is limit n tends to infinity 1 by 2 to the power n, that is 0. So for if x belongs to 0, 1, then this limit will be 0. Okay, for example this. Okay, so this is equal to 0 and for every x it is bounded. For every x, gx is bounded. So this is equal to gx into 0. So this is 0. Okay, if this is infinity at least 1x, then we cannot write this into 0 equal to, sorry, this is x, this into 0 equal to 0. If at least 1x, this is infinity, then we cannot write this because of G is bounded on 0 1, because of G is bounded on 0 1, we write this into 0 equal to 0, because this is not an infinity. Okay, so the real sequence fnx, where x belongs to 0 1, converges to 0 as n tends to infinity. So the sequence of function is pointwise convergent at x for all x belongs to open 0 1. Okay, and the limit n tends to infinity fnx equal to 0. Okay, for all x belongs to 0 1. Okay, so at x equal to 0, the sequence of function is pointwise convergent and the limit is 0. For x equal to 1, the sequence of function is pointwise convergent and the limit is g of 1. And for x belongs to 0 1, the sequence of function is also pointwise convergent and the limit is 0. So the sequence of function fnx is pointwise convergent. So the sequence of function is pointwise convergent. So the sequence of function is pointwise convergent on 0 1, and the limit function is fx equal to 0 for x belongs to 0 1 and g of 1 for x equal to 1. Okay, yes, for x equal to 0, limit is 0. For x belongs to 0 1, the limit is 0. But for x equal to 1, the limit is g of 1. So for x equal to 1, the limit is g of 1, and in the other part f of x is 0. Okay, so this is the limit function for the sequence of function. Clear? Now note that now we have to prove that if the sequence of function is uniformly convergent, if and only if g of 1 equal to 0. So first we take this is uniformly convergent, then we prove this, and then we take this and prove this is uniformly convergent. So first we take fn is uniformly convergent. So our pointwise limit is this. Okay, so first we take let the sequence function is uniformly converges to f. Okay, clear? Since each fn is continuous, here we write fnx is continuous on 0 1 for every n belongs to n. So each fnx is continuous. So since each fnx is continuous on 0 1, okay, so each fnx is continuous at x equal to 1. Okay, each fnx is continuous on 0 1, so at x equal to 1 is fnx is also continuous. Okay, for each n, as this is uniformly converges to f, therefore the limit function f must be continuous at x equal to 1. Okay, because in previous classes we discussed a consequence of uniform convergence, that this, if the subset of R and fn be a sequence of function which is uniformly converges to the function f. Okay, the sequence of function fn is uniformly converges to the function f, and each fn is continuous at C. This implies the limit function is also continuous. So here each sequence of function, each function is continuous at x equal to 1, and the sequence of function is uniformly convergent to f. So the limit function must be continuous at that point, that is at x equal to 1. So this is our fx. So if f is continuous at x equal to 1, then the left hand limit at x equal to 1 must be equal to f of 1. So this implies limit x tends to 1 minus fx must be equal to f of 1. Okay, because of continuity of f at 1, so limit x tends to 1 minus fx will be 0. So this is 0, and f of 1 means at x equal to 1 f of x equal to g of 1, so f of 1 is g of 1. So this implies g of 1 equal to 0. Okay, so we take if n is uniformly convergent, then we can prove g of 1 equal to 0. So the first part is done. So the first part of this problem, if n is uniformly convergent, if and only if g of 1 equal to 0, the first part is done. So now the converse part. Now we take g of 1 equal to 0 and we prove f n is uniformly convergent. Okay. So the converse part. Conversely let g of 1 equal to 0. Okay. Conversely let g of 1 equal to 0. Now we will prove. We have to prove that the sequence of function is uniformly convergent. Okay, uniformly convergent. So first we apply the MN test. What is our MN test? MN test. See the previous class says we discuss the MN test. We write in short, if this is a sequence of function and this is pointwise converges to f. Okay, this is a sequence of function which pointwise converges to f. If mn equal to supremum of x belongs to d mod of fnx minus fx. Okay, if mn equal to supremum of x belongs to d mod of fnx minus fx, then f is uniformly convergent if and only if limit n tends to infinity mn equal to 0. Okay, that is the sequence mn converges to 0. Okay, we repeat this test. If fn is a sequence of function which is pointwise converges to f, and if mn equal to supremum of x belongs to d fnx minus fx mod of, okay, then f is uniformly convergent if and only if the limit is 0. So in first part we find the pointwise convergent limit. Okay, we find that the sequence of function is pointwise convergent on 0, 1, and the limit function is this. Okay, so this part is already done. This is pointwise converges to f. Okay, so therefore since the sequence of function is pointwise converges on 0, 1, and the limit function is fx equal to, and the limit function is fx equal to 0, x belongs to 0, 1, and g of 1, x equal to 1. Okay, now for in this case g of 1 equal to 0, so this is equal to 0 for all x belongs to 0 1 because of the g of 1 also 0. Therefore the limit function is fx equal to 0 for all x belongs to 0 1. Clear? Now we find mn. Now our mn is mn equal to supremum of mod of fn x minus fx x belongs to 0 1. Here d is 0 1. Okay, so this is equal to supremum of x belongs to 0 1 mod of fn x. Okay, mod of fn x, because fx is 0, limit function is 0. This equal to, this can be also written as mod of fn x such that x belongs to mod of fn x such that x belongs to 0 1. Clear? Mod of fn x such that x belongs to 0 1. Clear? So if we have to find the supremum of this set, if we take the set A as fn x mod of fn x such that x belongs to 0 1. Okay, if we take A equal to this, so then we find the supremum of A. Okay, we find the supremum of A, since each member of A are greater than equal to 0. Okay, every element of A are greater than equal to 0, that is non-negative. So the supremum also greater than equal to 0. So the supremum is also greater than equal to 0. And since at x equal to 1, x runs over 0 1, and since at x equal to 1, fn 1, this is equal to g of 1 into x to the power n, because fn x equal to, because in our problem fn x equal to gx into x to the power n. Okay, so fn 1 equal to g of 1 into 1 to the power n. Okay, that is g of 1, here in this case g of 1 equal to 0, so g of 1 equal to 0, that is 0 into 1, that is 0. So at x equal to 1, fn 1 is 0, that is, and x runs over 0, so at x equal to 1, fn 1 is 0. So, and every term of this set are non-negative. Clear? So from this discussion we can say that the supremum of mod fn x does not attain at x equal to 1. Okay, because at x equal to 1 the value is 0, and every member are non-negative, so the supremum is not the value 0, bigger than 0, and at x equal to 1 the value is 0. So the supremum of fn x does not attain at x equal to 1. Okay, so in other words the supremum of mod fn x is attained at 0 1 open 1 because at 1 the supremum does not attain. Okay, so on this interval only on this part the supremum may be attained. At x equal to 1 the supremum does not attain. Okay, so Mn is supremum of this and supremum mod of fnx, and we find the supremum of fnx does not attain at x equal to 1. Okay, clear? Since fnx is continuous, we see in previous, okay, in the first part we see fnx is continuous. Okay, so fnx is continuous, okay, on 0 1. Clear? This implies fnx attains the supremum value. Okay, fnx attains the supremum value. Okay, that is there exists C belongs to 0 1 open 1 because at 1 the supremum does not attain. That is, there exists C belongs to 0 1 such that supremum of mod of fnx x belongs to 0 1 equal to fnc. Okay, because f is continuous on a closed and bounded interval. Fnx is continuous on closed and bounded interval. So we write a result. Every continuous map on a closed bounded set is bounded and attains its bounds. So the function fnx attains the supremum value. That is, there exists a point in 0 1, but at 1 the maximum does not attain. So we take this interval. So there exists a point in closed 0 open 1. There exists a point C in closed 0 open 1 such that at C the value will be supremum. Okay, clear? Therefore Mn, what is our Mn? Our Mn is the supremum of fnx. So our Mn is this, and this is equal to this fnc. Okay, and C belongs to closed 0 1 open 1. Okay, that is, this is equal to g of c into x to the power n, c to the power n, g of c into c to the power n. Okay, now limit n tends to infinity mn equal to limit n tends to infinity g of c into c to the power n. Okay, this is equal to, this is independent of n, so g of c into limit n tends to infinity c to the power n. Okay, because of c belongs to close 0 open 1, this limit tends to 0. So, and g of c is bounded, this is not infinity, so this is, the product is 0. Okay, we discuss in the first part. So limit n tends to infinity, mn will be 0. So by mn test, this implies the sequence of function is uniformly convergent to f. Okay, the sequence of function is uniformly converges to f. So we prove if fn is uniformly convergent, then g of 1 equal to 0, and if g of 1 equal to 0, fn is uniformly convergent. Clear? That's it. Thank you.